Alright, so our first old topic, and this is a really old topic, is going to be going over the atoms in the periodic table. So to start off, let's just talk about the basics of the atom. So the different components are the protons, which have a positive charge, the neutrons, which have a neutral charge, and the electrons, tiny little guys with a negative charge. Now, as far as size goes, protons and neutrons, these are the big boys of the atomic world. They both weigh in at about 1 AMU. So they weigh the exact same thing. They're much, much larger than the electrons. The electrons are tiny, tiny guys with essentially no mass. So when we consider their weight in the atom, they don't really affect it. It would be like a hair on your head. If you lose one hair on your head, you don't run and jump on the scale to see how much weight you lost because it's just one hair and it doesn't weigh that much. So an atom, if it gains or loses electrons, it doesn't really affect its mass because they're so stinking small. Protons and neutrons, though, those both weigh 1 AMU, so each one would count towards 1 atomic mass unit. Alright, let's picture an atom now. So an atom has two main parts. It has the nucleus and the electron cloud. The nucleus is the center region, and it's a heavy, densely packed area that contains the protons and neutrons. So that's then where all of the mass of the atom is, right here in the nucleus, because that contains the two things that actually have mass, and they're densely packed in that center region. On the outside of the nucleus, then, is the electron cloud, and we're going to draw as just a big egg-looking squiggle. But remember, this isn't going to be on the final, but remember that electrons are found in those orbitals that have the different shapes, the different regions, S, P, D, and F, the ups, the downs, all of that. We're just going to consider this as the area where the electrons are found. Most of the electron cloud is empty space because electrons are so small and they're so spread out, and it's a huge region. Most of the volume of the atom is actually this electron cloud. So if we were to visualize this on our level, this would be like a ping pong ball sitting in the middle of a football field, with the ping pong ball being the nucleus, the football field being the electron cloud. So the nucleus compared to electron cloud, huge difference in size. So the electrons are out there in an electron cloud, and there's usually just as many electrons as there is protons in a neutral atom. So we're going to go ahead and sketch 4 electrons out there in that electron cloud. Let's consider this on a periodic table square. So each square on the periodic table tells us stuff about a different element. And the pieces that are usually on the periodic table are the atomic number, which is always a whole number, the atomic mass, which is usually a decimal number on the periodic table, and then the symbol and the name. So the atomic number, the whole number, tells us the number of protons in the nucleus. So in the case of this atom right here, here's our nucleus, and there's 1, 2, 3, 4 protons. And so this particular element would have an atomic number of 4. The atomic mass tells us how much the atom weighs. So if we look at this guy right here, there's 1, 2, 3, 4 protons, and protons each weigh 1 AMU, so that's 4 AMUs worth of protons. And there's 1, 2, 3, 4, 5, 6 neutrons. So that's 6 AMUs worth of neutrons. So 6 plus 4, that means that this particular element would weigh 10 AMUs. And we're going to go ahead and say it's 10.0 since there's exactly 10 AMUs in that guy. And then last is the atomic symbol and name. So the symbol tells us what it is along with the name, and it's recognized by the number of protons. So atoms are recognized by the number of protons that they have. This particular guy has 4 protons, and so that means it would be beryllium. The number of electrons could change, the number of neutrons could change, but if you change the number of protons, that changes the element's identity. So you go by the number of protons to figure out what element it is. Now here's an issue that I know a lot of people are running into, and that's the changes in this number right down here. So if you go ahead and pull out your periodic table and take a look at beryllium, element number 4, and look at its box, you're going to see a little bit of difference there. So what you'll see on your periodic table is that the mass of beryllium is 9.012182. But the mass of the beryllium that we just drew is 10. So how does that work? This is where isotopes come into play. So isotopes are different atoms of the exact same element that have different masses. And they have different masses because they have a different number of neutrons. So neutrons in chemistry and the atomic world can actually come and go as they please. They can jump from other atoms, they can actually change into protons or change into electrons to do different things. So as a result, the number of protons or the mass of a particular atom can change. And so that means all berylliums don't have a mass of 10. They can have a mass of 8, they can have a mass of 11, they can have a mass of 12. And the number on the periodic table then is just the average of all of the different masses of beryllium based upon their abundance. So this number right here, the reason it's a decimal is because it's an average number of all of them. Let's consider, for example, three different isotopes of beryllium. So each of these beryllium nucleuses has to have 4 protons because that decides that it's beryllium. If it was 5 protons, then it would become boron. If it was only 3 protons, then it would become lithium. So we can't change that number right there. However, we can change the number of neutrons. So let's say, for example, that this one has 4 neutrons. And this one will give 3 to, and this one will go ahead and give 6 to. Now all of them are still beryllium because they still have 4 protons, but they have different numbers of neutrons. Neutrons aren't charged, they're neutral, so it's not going to affect the properties of the atom, it's just going to affect the weight, because each one of those neutrons weighs 1 more AMU. And each of them will also have those 4 electrons floating around outside in their electron cloud. That's what makes them neutral. If we look at the isotope notation gives either the symbol or the name of the particular element, and all of these are beryllium, and then a dash, and then after the dash we put the mass of that particular atom. So this first guy right here, it has the 4 protons and it has 4 neutrons, so then its mass is going to be 8. So that's beryllium 8. Now notice this number right here isn't the same as the number on your periodic table, and that's because this is the average. This is the mass for this atom right here. This atom right here that only has 3 neutrons but still the 4 protons that it's supposed to have, is going to have a mass of 7. And then this last guy right here with 6 and 4 will have the mass of 10. So then as a result, these right here are 3 different isotopes of beryllium. So 3 different versions of beryllium. Properties are pretty much the same, they just weigh different amounts. If you were to take all the berylliums and how much they exist in the real world, get the average of all those masses, that would be the number you put on the periodic table. So if you're given a mass in the form of an isotope notation, or you're told it weighs this many AMUs, go with that number. If you're not given the mass, use the mass number from your periodic table, and you can use that then to get your number of neutrons in the atom. Alright, so here's a chunk of your final review then that I gave you guys. Took out a couple things and actually edited something. So this last column right here where it had asked you for the ion symbol, but that's not going to really be on the test, so don't worry about that one so much. And then the aluminum, the number of electrons right there should have been 13. I think it said 25 on your guys' sheet. So let's do a couple of these together then, now that we've looked a little more at the atom. So this right here, this is hydrogen, and it has a mass of 3. So a lot of you guys are looking at your periodic table and say, no, hydrogen has a mass of 1. So remember, the mass on the periodic table is the average mass of all of the hydrogen atoms in the world. This is the mass of this particular hydrogen atom. So we're saying it has a mass of 3. So this one atom has a mass of 3. So how many protons does it have? Well, it's hydrogen. Hydrogen always has 1 proton. That's the atomic number. That's this number right there. The number of neutrons. So remember, this right here, the mass, is the number of AMUs of the atom, and it's made up from the AMUs of the protons and the neutrons. So if we have 1 proton, which weighs 1 AMU, how many neutrons do we need to get a mass of 3? Well, we would need 2 of them. So 2 neutrons plus 1 proton would give us a mass of 3. Electrons, 1 in this case, to match our 1 proton. That's what makes it neutral. And then our isotope symbol, that would just be the name hydrogen, or I'm just going to use the symbol so I can fit it in with a dash, and then the mass And remember the mass of this one is 3, so it would be H-3. So this would be an isotope of hydrogen that has a mass of 3. Alright, and aluminum with a mass of 28. So protons for aluminum, we can scroll down, and we could see aluminum, which is right over here. And notice how this mass number on our periodic table doesn't match the number up there. Remember, that's an isotope. So it has an atomic number of 13, which means it's going to have 13 protons. So we're going to have 13 protons. If it has a mass of 28, that means there's going to be 15 neutrons. And the symbol for this guy would be aluminum-28. And let's go ahead and do this third one together. So on this third one, we're not given the name of the element. Remember, the element is identified by the number of protons. Number of neutrons for this guy right here is going to end up being 76, because 128 minus 52 is 76 neutrons. Now we don't use this number right here, not the number of neutrons. Remember, that can change with different isotopes. We use the number of protons. So if we go to our periodic table and we take a look at element number 52, which is going to wind up being somewhere after 51. So right there, tellurium. Tellurium has 52 protons, so that's what it has to be. So we can come back up to our table, and we know that this element right here is tellurium. And its symbol would just be Te 128. Alright, hopefully that helps you out a little bit. Give these some practice. You should be able to find the number of protons, neutrons, and electrons using just your periodic table or information like this on the test.